Hello everyone, my name is Guy Katz and I'm a PhD student at David Arell's research group at the Weizmann Institute of Science. In this clip, we're going to see a demonstration of the WISE computing framework that we are developing being applied to a large-scale case study. The point of this demo is to show the usefulness of programming with an interactive and proactive companion that can draw the programmer's attention to interesting conclusions during development time. While our WISE development framework is still a work in progress, we show that it can already have useful insights about a real-world system. Our case study included the iterative development of a large system with the aid of the WISE development suite. We documented the development process, taking code snapshots at various steps. At each of these snapshots, we can see the conclusions that the WISE development suite draws from the code and the recommendations that it makes. Our experience shows that this form of development is useful and fun. It helps the programmer catch tricky bugs in the system during development time when they can still easily be fixed, and it also increases the programmer's confidence that the system operates as intended. So in this part of the demo, I'm going to briefly describe the system that we were developing in our case study, and in later parts we're going to focus on how the WISE computing framework analyzes it. For our case study, we chose to implement a cache coherence protocol. A cache coherence protocol is designed to allow multiple clients to access shared memory in a way that minimizes the actual read and write operations on that shared memory. So here we see a figure demonstrating the basic layout of our system. So on the bottom we have the shared memory. These are actual memory bits, and they reside on a shared bus. That's the blue line here. Now on that blue bus we also have our clients, the PCs, that can access the shared memory. So for instance, this PC here can ask to read a bit that's stored in this memory here. Now the idea is to minimize the number of actual read operations that are performed on the physical memory. So we have caches between the PCs and the buses, and these caches can store previous information and feed it directly to the PCs instead of rereading it from the memory bits. So for instance, if this PC reads this memory bit, then this read operation is physically performed once, and then if the PC attempts to read the same bit immediately after, then this bit is already stored in the cache, and the cache will give the answer to the PC without actually rereading it from memory. And the key fact here is that if another client then changes the actual memory, so for instance, if this PC writes a new value to the bit here, then other caches in the system, namely this cache, must be invalidated in order to ensure data consistency if this PC later tries to read this memory bit again. So now I'm going to show you our actual implementation for this cache coherence protocol. So our implementation was done using the behavioral programming framework, which is designed to allow programming reactive system using behavioral scenarios. And I'm not going to go into detail about behavioral programming. If you're interested, you're welcome to read more about it online. So as I mentioned, we took several snapshots of our code during development. This is one of them. This is snapshot number 5. And this is the main file of the program, and it describes all of the scenarios that we wrote. So in this snapshot, our system contains one bus with 2 bits of memory that reside on it, and 2 PCs that can read these 2 memory bits. So our scenarios include a scenario for each of the 2 memory bits, a few scenarios describing the behavior of each of the PCs, and then scenarios describing the 2 caches of the system. So let's have a look at one of them. Let's say we wanted to look at a scenario called cache 1 read fetch bit. So this scenario describes what happens when PC1 wants to read a bit from memory. So this is the main body of the scenario. We wait for requests, namely we wait for read events from the PC. Then we request the memory bus, we request ownership. Unless another scenario has already answered the PC, we then check the value of the actual bit. Then we release the bus, and then we answer the request. So this scenario demonstrates what happens when the memory bit needs to be physically read from the shared memory. And there are other scenarios that describe other aspects and other behaviors of the system. And if you want to see more, you're welcome to look at this snapshot and other snapshots, which are all available online. So now I'm going to show you what an execution of the code that we just saw looks like. So remember we were looking at snapshot number 5. So in snapshot number 5, not all of the functionality is implemented, but there's enough already implemented to make it interesting. So I'm running an execution, and we're going to see on the screen the trace log of this execution. Now here, the 2 PCs behave randomly. That is, they can issue write and read requests at random. So remember we have 2 PCs, so we have PC1 and PC2, and they can issue write and read events. So for instance here, PC1 issues a write event, it wants to write to memory bit number 1 the value 1. Likewise, there are read operations. So for instance here, PC number 2 wants to read bit number 0. And you can see, for instance, that after a read event, first cache should be consulted. So for instance, if PC2 wants to read bit 0, then we check what value is stored in cache 2. And here, bit number 1 is stored in cache 2. So bit 0 will have to be actually read in order to answer this request by PC2. In this part of the video, I want to demonstrate how the WISE development suite is integrated into the development cycle. Recall that each compilation of the code triggers the development suite. So still looking at snapshot 5, let's open the project. So I started a compilation, and this immediately triggers the development suite. It gets a fresh copy of the program and starts to analyze it. So right now on the screen, you see the output from the WISE development suite. This is just a summary of the output. There are logs in which the developer can read more details. And this window is meant to be opened during development. Personally, I always keep it on my second screen, which isn't being recorded right now. And it gives interesting information immediately during development. Okay, so you can see that everything happens quite quickly here. And the idea is that the developer can take this information immediately into account. And the output that we see here is from the offline part of the analysis tools, namely the sisters Athena and Regina, on which you can read more in the paper. But briefly, this analysis does not run the system, it only simulates it using an abstract model and provides both formal and semi-formal results. So let's have a look at the kind of information that is displayed in this log. The first thing that Athena and Regina attempt to do is to realize which threads have been programmed in the current snapshot of the code and how these threads correlate and correspond to one another. Basically, what they're trying to do is to recognize certain design patterns that exist in the code and leverage this information in partitioning the program into logical modules for later analysis, abstraction, etc. So the first information that we see in the log is a characterization of certain design patterns that are identified in the code, even if the programmer did not have this in mind. And this actually happened to us more than once, that we were, without knowing, actually implementing a certain design pattern. So you can see here various sensor threads that are identified, actuator threads, semaphore threads, and threads that use them. And I'm not going into any of these details, but you can look more at the actual code that's available online. We recognize certain array cells. This is actually some sort of shared memory implementation, also a design pattern, etc. And then what we see here in this part of the log is that the system attempts to characterize the actual logical modules based on all the information that it has gathered before. And in this particular snapshot of the code, there is only one bus implemented. So you can see a whole bunch of threads that deal with this memory bus and the caches that monitor it has all been grouped into one module, while the memory bits in the system, these are the actual memory, has been put in different modules, and we have also another module for a logger. We're going to see a more interesting example shortly. So what we see here at the bottom is that having finished the initial analysis of the system, Regina comes up with a list of emergent properties that it thinks may be relevant to the programmer, and then it has Athena prove or disprove them using model checking. So for instance, the first property that you see here is consecutive cache to request 1 events are separated by release 1 events. So what does this mean? It basically says that if you have 2 consecutive events of type cache to request bus 1, this is cache 2 taking ownership of bus 1, then these 2 events need to be separated by a release bus event. This basically tells us that we have correctly implemented a mutual exclusion protocol here, that in order for a cache to request ownership over a bus, that bus needs first to be released by the previous owner. So this is indeed an interesting property. So it's cool that Regina was able to come up with this and prioritize. As we explain in the paper, these emergent properties are prioritized, and we start with properties that may be more interesting to the programmer. So it's nice both that this property was defined and that it was prioritized as it was. And you can see here that this property holds. This was proved by model checking. And as you can see, this is an ongoing process. Athena and Regina constantly prove or disprove additional properties as the system is running. In this part of the demo, I'm going to demonstrate a typical instance in which the WISE development suite helped us, during the development of the cache coherence protocol, to identify subtle concurrency-related bugs. So let's have a look at the fourth snapshot of the code. Here, we had just finished implementing the caches for the first time, and then we played a bit with the system manually, and we felt that the functionality that we implemented was correct. That is, after every read event in the system, both caches were getting updated to reflect the recently read information. So we felt that things were behaving as expected. And then we asked Regina to also have a look. So let me compile the code. This will automatically trigger the WISE development suite. Now, remember that when the WISE development suite runs in autopilot mode, Athena and Regina begin to check emergent property on their own. However, there's also an interactive mode, and we found this mode much more useful once we had finished implementing new functionality in the system. This interactive mode lets the programmer specify which emergent properties should be checked manually. So here is the interactive window, and I'm going to bring Regina's output window as well. And let's ask Regina to check for emergent properties. So this is the list of emergent properties that Regina came up with. And here we see one that particularly draws attention. And this is it. It says cache 1 gets updated to mem0 equals 0 whenever there's a mem0 equals 0 event. So this is the read event from actual memory, and this is an update event of the cache. So here Regina was able to define a property that really does fit what we had in mind, right? We wanted to see that the cache functionality was correct, that the caches get updated whenever this memory bit is read. So Regina was able to accurately come up with an interesting property. Now let's ask her to check it. So here we have various checking methods that Regina can take. Right now we're going to use model checking. Later in the video we're going to see an example of model checking with abstraction, and there's also a bunch of other operations. And once we click OK, Regina is going to send this information to Athena for her to perform model checking, and then she'll give us the answer. So it was almost instantaneous. Okay, and this is the answer. So we see model checking based proof that the property does not hold. So basically Athena ran the model checking. She came up with a counterexample showing that the property does not hold, and now this is displayed right here. So let's see. Remember, we wanted that every mem0 equals 0 event to be followed or to appear very close by to cache 1 gets set to mem0 equals 0. So let's have a look towards the end of the run. We'll probably see an event of this kind without the cache being updated. So this seems to be the last mem0 equals 0 event. And let's try to figure out what's going on here. So we see PC1 reads bit 1 and PC2 reads bit 0. Now, if cache 2 contains bit 0, then it will answer the PC. But we see that cache 2 contains the information mem1 equals 0. So bit 0 needs to be read, and it is read. And cache 2 gets updated to reflect this new information. That's good, but where's cache 1? Why doesn't it also get updated? So PC2 gets the answer, and then it reads bit 1. Now cache 2 contains bit 0 because it was recently updated, but we need to read bit 1. So bit 1 is read. And now we see that cache 1 gets updated to bit 1 instead of bit 0. So here we see the problem. This is a sort of race condition where, because there are two consecutive read events by PC2, I'm sorry, this one and this one, the first event is overridden by the second without cache 1 being updated in time. So that's the problem. And this bug that Regina was able to find for us demonstrated what should be fixed in source phase 5. And indeed, in the next snapshot, you can see the bus arbitration mechanism that prevents this sort of race conditions. So this is one example out of many in which Regina was able to point out undesired behavior in the system, and we found this manual testing to be quite useful every time we finished implementing new functionality, whereas for the rest of the time we could settle for the autopilot, which was also useful. For the last part of this demo, we're going to see what happens when we run the WISE development suite in interactive mode on a more complex example. So let me switch to a later snapshot of the code, one that has more of the functionality already implemented, and I'm recompiling the code. Okay, so in a second we're going to see the analysis as before, only this time, as we can see, there are more threads and more functionality. So for instance, you can see that we have more modules that were recognized, one module that gathers all the threads that handle the functionality about the first bus and the PCs and caches that monitor that bus, and a second module that deals with a new bus that's also now implemented in the system. So you can see multiple buses. And now we can open our interactive menu. Okay, and this allows the programmer to specify what he or she wants the WISE development suite to focus on. So let's suppose we want to check an emergent property. And we have here a very long list of properties that the system came up with and which we can check. And let's suppose we want to check this property here. Okay, so I can click OK, and now the system asks me how I want this property tested. So for instance, I can do traditional model checking or model checking with abstractions, random testing, to add a monitor thread, etc. So let's suppose I want to do model checking with abstraction. And now you can see here in the log that the system is attempting to abstract away threads and modules which may not pertain to the property at hand. So basically, it's trying to abstract away information that's irrelevant with the hopes of making the model checking phase go more quickly. So for instance, the property that we're testing here is a property about the first bus. Okay, so we have memory bit 0 is set to 0 and release bus 1 events and their connections. So this is all about the first bus of the system. So you can see that the threads that deal with the second bus are abstracted away, and also a bunch of other threads which are irrelevant. Oops. And you can see here that the conclusion is that the property holds. And I can tell you that if we didn't do this in an abstraction way, if we did explicit model checking, it would take much, much longer. So this really is a very nice example of the spirit of WISE computing. The WISE development suite on its own came up with an interesting property that's relevant to the developer, and then in order to be able to model check it quickly enough to be relevant, that is to affect the programming as it's being conducted, it leveraged its understanding of the program and abstracted away irrelevant parts. And this understanding was obtained by analyzing the code and recognizing patterns within it without any annotations by the programmer, and this enabled the framework to characterize the logical facets of the program. While here I chose the property to be checked manually, this could also be done automatically by the framework if we left it in autopilot mode. In this video, we saw a few select instances from the Cache Coherence protocol case study where the WISE development suite was able to help the developers by finding bugs or by proving that the system indeed behaves as expected. We hope that this gives the viewers a taste of the many benefits of having the computer participate in the development process more proactively. If you want to learn more, I encourage you to download the Cache Coherence case study and the WISE development suite, which are both available online.